All right, we are recording, so you know. David, because of work responsibilities, has a hard time being here on Mondays. So typically record Monday's class and post it on XYZ somewhere. All right, it's good to be back. Looks like everybody's working away. All right. I think what we're going to do is review for the exam first, and that'll take a half hour or so, and then we'll have time for some questions afterwards. You can ask questions, and if you don't have any questions, we can find a problem or two to solve, whatever seems like the right thing to do. So I think all but one of you are in my Calc 1 classes, and the exam format's going to be the same. And I'll remind you, in case you forgot, there is a strict time limit. I try to write exams so the first couple of problems are easy. You can kind of build up momentum, feel good about yourself as you move into the more interesting problems. If it turns out the first problem's hard, like, don't panic. Maybe it just means you're missing some little thing. But don't panic, that's the worst thing you could do. Because there is a time limit, then my advice is to find a problem you can do and do it. If you read a problem and you think about it for 30 seconds and you don't feel like you have a good idea, then skip it. Make sure you get all the way through the exam, earning all the points that you're well prepared to earn. And then go back and work on any problem you might have had to skip. Because at some point, I'm going to say it's time to hand your exams in. I will come a few minutes early. I'll let you get a head start. Let's see, this class was at 2, so somewhere around 2:55. The time will expire, and you'll need to hand in your exam. All right, the next thing, like we always show work. The answer is not so important. It is important, but it's not the whole thing. And an answer with no justification is not worth very much, maybe nothing at all. Now, with that said, sometimes I'll ask a question where if you know what you're doing, like the answer is obvious. You don't have to do a bunch of calculation. You can just write it out. And if I ask a question like that, I know that I asked a question like that. And so don't feel like you need to write. If it's obvious, you don't need to write me a big long story about why it's the right answer. But most of the problems, there's going to be some work for you to do. I want to see the work leading up to what you submit as your answer. No calculator. It's actually good news for you all. That's some pretty nasty problems if you have calculators. We'll just focus on the concepts. It'll be typical on this exam and maybe the next exam as well for me to ask you to find an integral whose value is some quantity, volume or arc length or whatever, and not actually ask for the value. I mean, if you watch the videos, then I think more than once I said, like, finding the right integral, that's what we're all about. Chapter 2 of the book, that's what we're working on. Once we find it, then we basically reduced it to a Calculus 1 problem, except that we're starting to learn new antiderivative techniques. So once we move to the new chapter, then evaluating it becomes part of what we're all about. I think I did one example on the video where to calculate volume, we had to integrate by parts. Is that true, maybe? Yeah, so once we move into chapter 3, then evaluating it can be part of this class. But most of the problems, so pay careful attention. If I'm asking you to find an integral, but not the value, then I'm not going to think very much about how long it takes you, or how much effort, or how much you need to know to find the value of that integral. And if you go charging on ahead to get the answer, you're kind of wasting time that could be spent. If you want to do that, and I don't blame you, then make sure you've done all the work you need to do on all the problems, and then come back. For example, especially the washer method where there's a subtraction. If you set it up right, you should never, ever get a negative answer as your final value. I mean, volume, the way we talked about it, it's a positive quantity. So maybe you're a little nervous about how you set it up, and but you think, there's an 80% chance you got the right integral. Finish all the tests, but I didn't ask for the value, so you don't have to do it. Finish all the tests and then come back and just integrate it, just to make sure that you get a positive value. So read carefully. Find an integral versus find the volume. It says find the volume, then you find the integral, and then you integrate it. Fundamental theorem, do the arithmetic. All right. And the fourth thing is you can bring a 3x5 note card. You can write anything you want on it. You don't need to hand it in. You probably don't need to save it, except it might help you study for the final, the detail that you wrote on. Anything you're nervous about, if you watch the videos or in class, sometimes I'll ask you to memorize something. Because when we do the derivation and it's maybe it's complicated and it's fun, it's challenging, but you don't want to go through it again. So I say memorize it, and until we really have it like fully 100% memorized, you can just write it on your note card, and then it'll be there when you need it. I'll remind you of a few things. We have some formulas here. We have also an antiderivative. When you read a problem, pay careful attention to exactly what I'm asking you to do. Somewhere, there may be a lot of words, and somewhere there is a verb. Find, or calculate, compute, graph. There could be lots of words, and so make sure you know exactly what I'm asking you to do, and do that to the best of your ability. All right, so the material, pretty simple here. We've only been in 2 chapters. We have chapter 2, which applications. Because I was gone, we didn't work all the way through some of those I want to do in person. The ones we have talked about, first of all, is area between curves. The formula ends up, the function on top, I'll call it that. Minus the function on the bottom. I've seen students get, once we learn the volume techniques, to get confused between area and volume. Remember, especially the disk washer formula has squares in it. Well, those squares are because there's a radius involved, right? And the area of those circles, pi r squared. That's why the squares are there. They never show up as a formula on area. Now, the function f, it could be x squared. It could be have the form of a square, but the formula doesn't tell us to square it. So remember, integral of functions we think of as area. If we take the function and we square it, then maybe, it's volume if we set it up exactly right. Some of the problems, you were given A and B, some of the times you had to solve for it, right? So be prepared for either one. Then we went on to 3 different volume techniques. The first one was where we know the cross-sectional areas. Probably the hardest one because the formula is real generic. You have to find an area function. And we're told the areas all have a common shape, rectangles or triangles. If they're triangles, we need more information, like equilateral, semicircles, whatever. But if we can find that area function, then we just need to integrate. And then we use that technique to get us the disk / washer method. And formulas here look like pi integral a to b f of x squared. The function represents the radius. If you look inside here, you get the volume, like of a cylinder, pi r squared h. There's the pi. The radius is continuously changing. That's why it's an integral problem. Then h would just represent the height and so on. So that the function gets squared because it represents a radius for us. And then the washer method, you just take the area of the outer circle, f of x squared, and then subtract the inner. A couple of formulas there. And finally, we looked at the shell method. And the constant was 2 pi, the integral a to b x f of x. I hope you watched the video, the explanation for finding the Riemann sum, because you got to be pretty creative. It didn't, the ingredients we need, delta x and so on, they didn't show up automatically. We had to do some work, which justifies the two. Notice there's no square here. The square only shows up on this washer method. Also, of course, when you say this, we learn how to use functions of x or y. I've written the formula as if they were using functions of x, but don't have enough experience that we can look at a problem and say, well, this is going to be easier if we use functions of y. And for this formula, for shells, we're going around the y-axis for it to be, and let me emphasize in a different color. The axis of rotation is the opposite of the variable of integration. Whereas for the disk and shell method, for this formula, it's for rotating about the x. And in this case, the variable, the axis of rotation and the variable, they're the same. So the way you solve it sort of generically, the volume problem, you sketch the region. I'm talking about a revolution, not the first technique. You sketch the region, and then you look at the region and say, do I want to use functions of x or functions of y? Okay, so you make that call. Sometimes it doesn't matter. If it doesn't matter, we probably use functions of x, right? But you make that decision, functions of x or y, and then you say, what's the axis? Is it the x or the y? So let's say we choose y over here, but it's going around the x. Then what technique are we going to use? Shells. Yeah, they're the opposite. Okay, and when I realize it's shells, and I say, oh, I don't want to do that. Let's go back and describe the areas of using functions of x. It might require 2 linears. We know how to make those decisions. All right, and finally, we had a section called arc limit. So we have a function, and we want to know how long is the curve. If we travel along the curve from some point to another point. And there's no pi's here, there's no rotation, nothing circular. And again, we had a fairly interesting derivation to get the Riemann sum. I hope you read through it. We had to remind ourselves, or maybe learn for the first time, the theorem from Calc 1, the mean value theorem, but it came into play. Notice that the function itself doesn't show up in the formula. That is, if I take a function like this, here's my f, and I add a constant to it, and I go from a to b, how do the lengths compare? They're exactly the same. Yeah, it doesn't matter what the functional values are. It only matters their relationship. And the derivative tells us that, like how fast is it increasing every point. The derivative has all of that information. And therefore, the derivative is involved in the formula, not the function itself. Okay, it's kind of good news, bad news here. The good news is we got a formula for arc length. The bad news is for most functions, even simple ones, we can't evaluate that integral by the fundamental theorem. The antiderivatives are complicated. In some cases, it's because we haven't learned all of chapter 3 yet, where we learn more techniques, right? We're learning some as we go. And sometimes it's because they're just nasty. In fact, the functions that you can actually apply the fundamental theorem to for arc length, there are not very many, and they're kind of weird. I did one on the video, e to the x plus e to the minus x over 2. I hope you watched it. I think I assigned one or two, but the one I did in the video, x squared, like the simple function x squared, the integral we didn't know an antiderivative. We will learn one, I think it's the very next section once we get through exam 1. But we don't know one so far, and therefore it just became a calculator problem. Of course, I know you don't have calculators, so when I make up the exam, I'll keep that in mind when it comes to ArcLink. But actually, for the whole exam, for the spectrally here. All right, and then we did some things out of chapter 3. We, first of all, briefly, quickly reviewed everything we knew about antiderivatives. And then we added a new technique, the so-called biparts. And the way to think of it, the way that I think of it, is we split the function into these two pieces called the mu and dv. And once we make our choice, whatever we label u, we find du, the derivative, times du. And whatever we label dv, we need to integrate. Because the d says this is down a derivative, to cancel that d out, we need to integrate and come up with our v, and then we put the pieces together like this. And what we really hope is that this guy is easier, we'll say known. The guy we started out was unknown. But we can trade it, and hopefully this guy's, we can get it, and if we can get it, then we can find this guy's antiderivative. It's sort of like an indirect way, but it's perfectly valid. If we make our choice for u and dv, and this integral seems more complicated than that one, then it just means we made a bad choice. Doesn't mean it's not solvable. Go back and start all over. Be willing to admit, like, you look at this guy and say, wow, that's terrible. Just scratch it, go back and make a new choice for your u and your dv. Calculate du, calculate v. See if you don't get a better integral. All right, and finally, we talked about trig integrals. Two different varieties. Similar. The first one was sines multiplied against cosines. And I gave you some strategies. If one of those powers is an odd positive number, then we know exactly what to do. We may not want to do it if the odd positive power is very large, but we know exactly what to do and it'll work 100% of the time. And then we had a similar one where we had tangents multiplied against secants. Which is a little more complicated because the derivatives, we're thinking about eventually substituting. And therefore we have to think about derivatives. Well, the derivative sine is cosine, the derivative cosine is sine times -1, but real similar functions. Right? The minus sign doesn't create any complications for us. On the other hand, with tangents and secants, it's not the same kind of function, it's different ones. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Yeah, it's different. And so think carefully about it. If you watch that video clear to the end, I gave you some advice. If you start with a tangent and secant and you just don't see a way to figure it out, then convert to sines and cosines. We're just more comfortable with sines and cosines. And you can do it. Tangent is sine over cosine. Secant is 1 over cosine. So you can rewrite it totally in sines and cosines. And then because we're more comfortable, because they're simpler, maybe we can come up with a good idea. Maybe we'll get an odd positive power. And then we have a guaranteed way to find the antiderivative. Okay, if you did the homework, I think the next to the last problem, you were surprised to see something like this. I mean, you all probably got slightly different ones, sine 5x, cosine 3x. Where these numbers are different. 5 is not the same as 3. That's a big complication. We can't just easily substitute the 5 or the 3 away. We could get rid of one of them, but not the other. And there are some identities that help us find antiderivatives here, but I didn't tell you about them in the video because I didn't want us to worry about these. And then I don't know how it happened, but maybe let's just say I was hurrying to visit my dad. That's not true, but give you some excuse. I shouldn't have assigned that problem. I didn't prepare you for it. A lot of the integrals were used identities that we're super familiar with. I hope the Pythagorean identities, you know that. Double angle identity we used, you guys all know there are double angle identities. If you don't, some of you haven't, maybe know what they are, you haven't memorized, some of you don't. But the ones to evaluate this are less, they're more obscure. And so I didn't want you to deal with this. Thank you, Daniel, for letting me know and for recognizing that it was a problem. And as soon as the deadline passes tonight, I'm just going to go through and give everybody full credit for this problem. Okay? And in fact, just don't work on it anymore. It won't help you for the exam. It will only frustrate you. Just wait for me to give you a point. All right, and then there are a couple of results that came out of here that I've asked you to memorize. And hopefully you're on your way. And of course, on this exam, memorize may mean get it on your note card. And that is the antiderivative of sine squared. I asked you to memorize it for 2 reasons. Number one, it's if you just say, oh, I think it's this, you'll be wrong 100% of the time. I started to say it's complicated. It's not, but we have to be careful, and it's not obvious. And here's what we get: 1/2 theta minus 1/2 sine 2 theta. If you remember, we used the double angle for cosine. Cosine 2 theta. There are 3 versions of it. The one that works for this one is 1/2 times 1 minus sine 2 theta. That's the double angle. And hopefully it's at least vaguely familiar to you from your pre-calculus work. And then we just solve for sine squared and made it. So we get, in terms of sine squared, we get a cosine, and then we integrate that. That's where the sine comes from. Okay. Very similarly, if we change sine to cosine, but you don't have to know how or why it works out. But you need to know these results one way or another. Memorize it on your card. Surprisingly, the only change between these is that sign right there. Everything else stays the same. So that sign, it's still the sine function, not the cosine. I mentioned that what makes this problem unsolvable for us, based on what I've presented to you, is the fact that these multiples are different. If they're the same, like hopefully, if you see this problem, you'll say, yeah, I know exactly what to do. Sine 5x, cosine 5x. When they're the same, then there's no problem whatsoever, because we can substitute them away. We'll let u be 5x, and then du is 5 dx. And so that 5 I need to divide by it, I get a 1/5, and then sine u cosine u. When they're the same number, you just substitute them right away. You can do the same thing here. We have multiple Don't try to guess how it's going to affect this, because most students will get it wrong. Just substitute it away. Take one step before you launch this thing we memorize. Make a substitution, get the constant out of there. Trade the x for a u, and what happens is you'll get a coefficient out here, and then you'll get it in the form that you can use the result that we're memorizing. Okay? The only exception is if this is the opposite. We can handle that. The same value except one positive, one negative. Because do you remember the negative angle identities? Remember there is such a thing? Yeah, the minus sign we can pop out of the sign. Sine is what we call an odd function. It's symmetric through the origin. Does that make sense to you? Whereas cosine is an even function. It's symmetric across the y-axis. And so any minus sign inside here, it just goes away. It disappears. It's like x squared. The function x squared and the function minus x squared, the same function, right? Because minus x squared, that minus sign just goes away. Cosine has the same property. So that's the only exception. If these numbers are different, but they happen to be negatives, we can still do it. If they're not negatives, we don't know how to do it. It's an unfair question for me to ask. I guess I could say, here are two integrals, like evaluate one of them and have these for one, and hopefully you won't pick it. Noah.
Can there be two separate u's then for that problem?
No. Take the minus sign out by the identity, and then you can substitute for whatever's left.
I mean, like once you get the sine u, cosine u, isn't it u itself?
Oh, you're right. Yeah, so when we do a double substitution, what variable should we use? How about a double u? It's a map. dw is cosine u du, right? And so we get 1/5 sine w. dw, the antiderivative of sine is minus cosine. You're right. You're exactly right. Some of you, and it's perfectly fine with me if you can do it, can maybe do the substitution details in your head. You can say, look, here's a function. Here's its derivative. So all I have to do is raise the power by 1, divide. You can see that u du or w dw coming. And just raise the power. You don't have to spell out all the details. If you need to, absolutely do it. But maybe you can see without it. All right, that concludes the material for the exam. Are there any questions? So if you were in my Calc 1 class, and I think all but 2 of you were, Daniel was, but not last fall, you'll remember that I posted review problems. And I've done that again. I think I said it, but they'll open up at 4 o'clock this afternoon. And most of them are problems that make you feel like you've seen them before. The online homework, it only embeds so many problems in it. But you'll get different numbers, and you did some of them 3 weeks ago and probably forgot. I know that's hard to believe, but maybe it's true. And so work your way through those. I'm going to probably use some of them on the exam, not all of them. Most of the problems on the exam will be very similar to problems you've seen before if you've been doing the work all along. But I really like to ask one problem that's different. And I want to see, can you think creatively? We know all of this stuff, and now here's a problem we've never really seen anything quite like it. Do you see how what we've learned helped you figure out how to solve the problem? So, not very many. I like to say 90% pretty much like the homework you've encountered, and maybe 10% that be a little bit different. Not difficult, but just different. You get to think creatively. Our exams is not the best place to ask you to think creatively because you're feeling pressure, time pressure, material pressure. But for 10 points, maybe it's, yeah.
So when I was doing the homework, I didn't get the derivative of the secant x. Now that I'm looking at it, that's just secant squared x.
Which one?
Tangent x secant.
Just tangent times secant?
Yeah.
Yeah. It's just secant, is that what you said? Yeah. Because the derivative of secant is secant. Yeah. And it was in the homework? Any other questions? All right, I'm pretty sure I mentioned earlier, I'll say it again. You will be asked to find integrals. You will be asked to find quantities. Make sure you understand that you know the difference. What am I asking for? Underline the instruction. Because if I'm asking just for the integral, anything you do to evaluate it is a waste of time. Unless you're done and you're just checking. Okay? And also, if I ask you just to find the integral, then I don't really care. I don't think about how much time it would take you to evaluate it. And so if you do evaluate it, like it's possible it could chew up a bunch of time, and it's not going to help you. So careful attention, like underline in the problem, what exactly am I asking for? And focus all your energy there. And then later, you can think more if you have time at the end. Any other questions? Would you like to do a problem or two, or you feel good? Feel like you're ready to go? Okay. For my morning class, I took pictures of problems in the book and brought them. But this afternoon, I forgot to bring my phone, so let me see if I can make one up. The region under y equals the square root of x. From x equals 1, 4 is rotated about the y-axis. Find an integral whose value is volume of the resulting solid, which is solid, using the dishwasher method. Part A. Part B, the shell method. So, same region, the same solid. Show how we can use either method. All right, so y equals square root of x. Everybody knows what that looks like? Yeah, half parabola. We're going to go from 1 to 4. And then we're rotating about the y-axis. Which method feels the most natural to you? The shell method. So let's do B first. Constant for shells. I know you haven't made your 3x5 note card yet.
2 pi.
Integrate from where to where? What's our variable of integration?
1 to 4.
Yeah, it's x, and it goes from 1 to 4. And the formula says take x, that represents the radius of the shell, and multiply it by
The derivative of the function.
the function, square root of x. I ask for the volume or the integral. Jesse,
Isn't it times the derivative?
pardon?
Isn't it times the derivative?
No, the derivative is only involved on the arc length.
Oh.
Oh, right.
Yeah. Am I asking for the volume or an integral?
An integral.
The integral, yeah. So here's the correct answer. It gets me all of the points for part B. But there's some little part of me that wants to simplify it. Which set it up for integration. And if the problem asks to find the volume, then of course we need to do this to set it up for that antiderivative. Go over here so David can see it better. Any questions? All right, so for part A, just washers, we're going to integrate with respect to what variable? Why? Because it's going about the y-axis. The variable is the same as the rotational axis. So just put it in parentheses. Okay, and we're using, is it going to be discs or washers? Washers, yeah, we got this hole. The region doesn't make it all the way over to the axis. So what's the constant?
Pi.
I. Integrate from where to where?
From 0 to 2.
0 to 2. Perfect. Yeah, we don't have the 2 labeled. Oh, this is a bad question. Well, it's a little trickier than I thought. And I think Jesse's asking from, draw a line across there. The function on the bottom, functions of y, the function on the bottom is on the left. It's that line. Yeah, because it doesn't go all the way over here. So I just made this problem up on the spur of the moment, and maybe it's not the very best problem. Let's go from 0 to 4. It'd be easier to set up. And that's trivial to fix over here. Just change those 1s to 0s. Then we get our radius factor. Oh, good grief, Johnson. We're using dishwashers. The function to the right is this one out here, x equals 4. Squared, that's the radius, the same for all of the points. And then the inner radius is for each y value is the distance from here to there. So this curve is y equals the square root of x, and therefore what's x?
X squared. Or y squared.
Y squared, right function, wrong variable. And that's the radius, so the formula says you got to square that. This chain may be in the way of something. Okay? Does that make sense to you? Now, if I hadn't changed the problem, then our answer to B would, someone answered Jesse maybe. When I asked what's the natural way to do it, or maybe it was no, shells is really the natural way to do this. And to do it with disc washer, the way I originally asked the question, it would actually take 2 separate calculations because the function on the bottom changed. Down here is that constant function, and up above, it's the portion of the parabola. Yeah.
Why is it, why is 4 the function that we subtract the other function from? Because that was supposed to be the top one minus the bottom.
Yeah, so this function is on the top. And that function is x equals 4. For functions of y, to the right is to the top. It's a constant function.
Okay, so the way I do it is I like flip it in my mind sideways, kind of. So like if it was rotated 90 degrees to the right, then I'm like, okay, so it's 0 to 4. It's the x values of the y. Or 0 to 2, I mean.
So you flip it, if you flip it, you get that sort of a picture. The original problem, you get that sort of a picture. When it comes down to it, we've said this before, the variable of an integral is kind of a dummy variable. What matters is what is the function and what are the limits. It doesn't really matter what we call the variable. So it is possible to just reorient things. Yeah, I would need to see some evidence that that's what you're doing, like maybe a new picture. But if you just say, I'm not going to use functions of y, I refuse, then you can interchange. Of course, part B, perfect. You don't need it. It just works out perfect. Then for part A, you could show me enough so that I know that's what you're doing. Otherwise, how am I going to grade it? If I see x's in there, look carefully. But what matters is the function and the limits. Does that make sense? Any other questions? Should have picked a better example. Forgot to bring my phone. Yeah.
Could I just have a review of the cross-sectional volumes?
Sure. So I'll make up a problem and I'll see if I do a better job. Okay? Base of a solid. Is the area, the region, between y equals 16 minus x squared and the x-axis. Cross sections perpendicular to the y-axis are rectangles whose height is half the length. Find an integral. That gives the volume. I'd probably add a few more words if I was typing it. All right, 16 minus x squared is a
Downward
parabola lifted 16 units up and headed down. The intercepts are 4 and -4. I'm not sure if those are going to matter. So there's the base. Okay, so far? Cross sections perpendicular to the y-axis. So for every y between 0 and 16, we get these rectangles. That's the length. And then in the third dimension, this rectangle extends, which is half of the length of the base. So let's draw it out here. Blue. Here we go, red. Here's the length across from the bottom of the rectangle, and that corresponds to that distance in the picture. So it's clearly not a revolution. So those other formulas are no good. And what we need here is the area function. And I always like to start with the most basic, but we got rectangles. The area of a rectangle is length times width, or as we've called it over here, height times length. The length is the distance from here to there for any given line. Okay, so we have our curve. And to find how wide it is, we need the x coordinate. So let's solve that for x. I'll take the positive square root. So you give me a y value between 0 and 16, and then the x coordinate out on the curve, the distance from here to there is that y. Does that make sense to you? But the length across the base of the rectangle is double that. Right? You got to go clear across. So the length is 2 of those guys. But the height is half. And half of that is just one of those radicals. Does that make sense? And look what wonderful thing happens. Just get twice the square root of, no square root, twice 16 minus 1. So I look back to the instructions, find an integral. So the volume is the integral from where to where?
0 to 16.
0 to 16. Twice 16 minus. Okay, Scott? Yeah. If I would have asked for the volume, like that's a super easy integral to evaluate. But what if you got confused and you ended up with like a super complicated? Another advantage for me, just asking for the integral. Like if you make a mistake and it's supposed to be an easy integral, but because of your mistake, it's now a nasty one. If I just ask for the integral, you don't have to worry about dealing with the mistake. And then I can just, grade your mistake, where to go, how serious of a mistake it is. Anything else? All right, so lots of good things to think about. Look those problems over again. It should open up around 4 o'clock. And I'll see you as early as 1:55.